In August last year, NASA picked up a radio signal coming from our own sun, and for months afterward, the agency said almost nothing about it in public. No big press conference, no dramatic announcement, just quiet analysis behind closed doors while 4 different spacecraft kept recording the same strange broadcast over and over, refusing to stop. When scientists finally explained what actually happened, the answer turned out to be stranger than almost anyone expected, and it forced researchers to completely rethink what our own sun is capable of doing right above our heads. Let's start with what actually happened, because the real sequence of events is far more interesting than any invented mystery could ever be. On August 21st, instruments monitoring the sun picked up what looked, at first glance, like a completely normal event. Solar radio bursts happen all the time. The sun is an enormous, chaotic ball of plasma and magnetic energy, and it regularly throws off short bursts of radio waves as part of its constant, violent activity. Most of these bursts last a few hours. Some of the more unusual ones might stretch out for a day or two before quieting back down. Scientists who study the sun see this kind of thing regularly enough that a new burst rarely makes headlines on its own. But this particular signal refused to behave like every other burst before it. Instead of fading out after a few hours, it kept going. Then it kept going through the next day. Then the day after that. Scientists tracking it started checking their instruments, assuming something must be wrong with the equipment, because nothing in recorded solar history had ever lasted this long. It did not stop after 2 days, or 5 days, or even 10 days, by the time the signal finally faded away. An incredible 19 straight days had passed, shattering the previous record for the longest solar radio burst ever documented, which had stood at just 5 days. Think about that gap for a second. 5 days was already considered an extreme rare outlier in decades of solar observation. This new signal lasted nearly 4 times longer than that previous record, an event so far outside normal behavior that it genuinely stunned the research team studying it. And here's where the quiet part of this story begins. Because once scientists realized just how unusual this signal actually was, they did not rush to explain it to the public. Instead, they spent months carefully cross-checking data from multiple spacecraft, trying to understand exactly what could possibly cause a radio signal from the sun to keep broadcasting continuously for nearly 3 full weeks without stopping. Picture what that actually looked like from inside a research team's daily routine. Every single day, for 19 straight days, scientists would check their monitoring instruments, expecting the signal to have finally faded out overnight, the way every previous burst on record always eventually had. And every single day, for 19 straight days, the data showed the exact same thing. The signal was still there, still broadcasting, refusing to follow any pattern anyone on the team had ever seen before in their entire careers studying the sun. Some team members later admitted they initially assumed a piece of equipment must have been malfunctioning, since nothing in the historical record prepared them for a genuine, real event lasting this long. It was only after confirming the same unusual signal across several completely independent spacecraft, built by different teams and using different detection methods, that researchers finally accepted this was a real physical phenomenon and not some shared instrument glitch. This type of solar radio signal falls into a category astronomers call a Type 4 radio burst. These bursts happen when clouds of fast-moving energetic electrons get trapped inside massive magnetic structures in the sun's outer atmosphere, structures known as helmet streamers, so named because their shape resembles an old-fashioned pointed helmet stretching out from the sun's surface. Normally, these electron clouds disperse relatively quickly, releasing their burst of radio energy and then settling down as the trapped particles disperse or lose their energy. What scientists eventually figured out about this event was that the electrons somehow kept getting replenished, almost like water continuously refilling a leaking bucket faster than it could ever fully drain, creating what researchers ended up describing as something similar to a core-rotating electron reservoir, a persistent, self-sustaining pocket of energetic particles that kept spinning along with the sun's rotation and kept generating fresh bursts of radio energy for nearly 3 weeks straight. To understand why that matters so much, it helps to picture how the sun's outer atmosphere actually behaves. The sun does not rotate as a single solid object the way a planet does. Different regions of its surface and atmosphere rotate at slightly different speeds, and massive magnetic loops and streamers get twisted, stretched, and dragged around as this uneven rotation continues. A helmet streamer typically forms above a boundary between magnetic regions, pointing in opposite directions, creating a kind of natural magnetic trap capable of holding onto charged particles far longer than open regions of the sun's atmosphere ever could. What made this particular event so unusual was that the electron population trapped inside the streamer did not simply run down and disperse the way physics would normally predict within a matter of hours. Instead, something kept refreshing the supply of energetic electrons, feeding into that trap, keeping the radio emission alive far longer than any similar structure had ever been observed sustaining it before. 4 separate spacecraft ended up capturing this signal from different angles and different distances, giving researchers an unusually complete picture of an event that would have been almost impossible to fully understand, using data from just one instrument. Having multiple vantage points meant scientists could track exactly how the signal changed as it traveled outward, how its strength varied over time, and how it lined up with the physical structure on the sun's surface that was actually producing it. This kind of multi-spacecraft coordination does not happen automatically. It takes careful, deliberate scientific work to combine data streams from completely different missions into one coherent explanation, which is a big part of why it took so long for a full public explanation to finally emerge. Coordinating 4 separate spacecraft is genuinely complicated work behind the scenes, even though it sounds simple when described in a single sentence. Each spacecraft carries different instruments, built by different engineering teams, calibrated in different ways, and positioned at completely different distances and angles relative to the Sun. Before researchers can even begin comparing what each spacecraft recorded, they first have to make sure every dataset is properly calibrated against the others, correcting for the different travel times light and radio waves take to reach each individual instrument, and accounting for the fact that each spacecraft was essentially watching the same event unfold from a slightly different seat in the audience. Only once all of that careful technical groundwork is finished can scientists actually start building a single, unified timeline of what happened, matching up small variations in signal strength recorded by one spacecraft against similar variations recorded by another, gradually piecing together a 3-dimensional picture of an event that no single instrument could have fully captured alone. The formal scientific paper explaining this event was not published until this year, nearly 9 months after the signal was first detected. 9 months of near silence on the public side, while a small team of researchers quietly worked through the data, tested different explanations, ran the numbers again and again, and eventually built a case solid enough to publish in a respected scientific journal. That gap between the original detection and the final public explanation is exactly the kind of quiet period that naturally makes people suspicious, wondering whether something bigger was being deliberately kept hidden. In reality, this is simply how careful science tends to work. Extraordinary claims require extraordinarily careful checking before anyone puts their name on a formal explanation, especially when the event in question breaks every previous record on file. So why does any of this actually matter beyond simply being an interesting record-breaking curiosity? Because understanding events like this directly affects our ability to protect the technology surrounding our own planet. These Type 4 radio bursts are closely linked to the same magnetic conditions that can also produce far more dangerous space weather, including solar flares and coronal mass ejections, enormous eruptions of charged particles that can disrupt satellites, damage power grids, and threaten astronauts working outside the protection of Earth's atmosphere. The radio waves themselves are completely harmless to us here on the ground, but the underlying magnetic activity capable of producing a burst. This unusual and this long-lasting is exactly the kind of activity space weather forecasters desperately want to understand better, since predicting dangerous solar events, even a few hours earlier, can make the difference between satellites surviving a solar storm undamaged or being knocked permanently offline. Modern life depends on satellites far more than most people ever stop to consider. GPS navigation, weather forecasting, international phone and internet communication, and even the timing systems that keep banking transactions synchronized around the world all rely on satellites that sit directly in the path of dangerous solar activity. A single severe solar storm hitting Earth unprepared has the potential to knock out multiple satellites at once, disrupt radio communication for commercial airlines flying polar routes, and in a worst-case scenario, damage transformers within power grids on the ground, potentially causing blackouts lasting days or even longer in the areas hit hardest. This is not simply theoretical concern. History already includes real examples of strong solar storms causing serious disruptions, including one famous event in the 1800s that set telegraph systems on fire and lit up skies with auroras visible far outside their normal polar range. Understanding unusual solar behavior like this record-breaking radio burst gives forecasters valuable new data points, helping refine the models used to predict exactly when the next truly dangerous solar storm might be building. This is not the only mysterious signal quietly keeping scientists busy behind the scenes recently either. Around the same general period, astronomers using a powerful radio telescope array based in South Africa picked up an entirely different kind of signal, this time coming from something much stranger than our own sun. They detected faint radio emissions linked to a rare interstellar visitor passing through our solar system, a comet that had traveled here from another star system entirely. The specific radio signature detected came from hydroxyl molecules, essentially water breaking apart under sunlight, streaming off the object as it warmed up during its journey through the inner solar system. Detecting this signal took multiple attempts. 2 earlier observation windows came back with nothing detectable at all, and only on the 3rd attempt did researchers finally manage to confirm the faint radio signature they had been hunting for. The reason it took 3 separate attempts to detect this signal comes down to just how faint it genuinely was. The interstellar object was still relatively far from the sun during the earlier attempts, meaning less sunlight was hitting its surface, which meant less water and gas were being released into space, which in turn meant a much weaker radio signature for the telescope array to try to pick out from all the background noise filling the sky. Only once the object moved close enough to the sun to start warming up significantly did its outgassing increase enough to finally produce a signal strong enough to clearly detect. Researchers had actually planned for this possibility in advance, deliberately scheduling multiple observation windows spaced out over several weeks, specifically so they would have more than one chance to catch the signal once conditions became favorable enough, rather than relying on a single all-or-nothing attempt. That pattern of repeated, failed attempts, followed eventually by a successful detection, shows up again and again throughout modern astronomy. And it is worth understanding clearly, because it explains a lot of the apparent silence that often surrounds these kinds of discoveries. Scientists frequently point their instruments at a target multiple times, come back with nothing usable, and simply try again during the next available observation window, rather than announcing every single failed attempt publicly. From the outside, that process can look like secrecy or silence. From the inside, it is simply the normal patient rhythm of real observational science, where confirmed detections are genuinely rare and failed attempts vastly outnumber successful ones. There was even a moment during that same interstellar object's journey when a NASA spacecraft called Juno, currently orbiting Jupiter, prepared to use its own onboard antenna to search for a radio signal coming directly from the comet as it passed unusually close to the giant planet. This kind of opportunistic science, repurposing an instrument built for one mission to attempt a completely different kind of detection, happens more often than most people realize. And it shows just how resourceful scientists have become at squeezing extra value out of spacecraft that were never originally designed for the exact task being asked of them. Meanwhile, other categories of mysterious cosmic radio signals continue to challenge astronomers in ways that go far beyond our own solar system entirely. Fast radio bursts, incredibly brief flashes of radio energy lasting only a few thousandths of a second, yet somehow releasing as much energy in that instant as our own sun produces across an entire year, remain one of the strangest unsolved puzzles in modern astronomy. Some of these bursts happen only once and are never seen again from the same location. Others repeat, firing off multiple bursts from the exact same spot in the sky over weeks, months, or even years, a pattern that has helped rule out certain violent one-time explanations like a single catastrophic stellar explosion, since something clearly keeps surviving and firing again afterward. The leading explanation currently favored by most researchers points toward magnetars, an extreme type of collapsed star with a magnetic field so powerful it defies easy comparison to anything found naturally here on Earth. Some of these repeating signals appear to originate from magnetars that may exist in binary systems, orbiting closely alongside a companion star or drifting through a dense cloud of surrounding plasma. Interactions that could help explain why the resulting radio bursts often look so irregular, intense, and difficult to model using any single simple theory. NASA's own X-ray telescopes have managed to catch at least one of these events in extraordinary detail, observing the exact moments immediately before and after a burst fired from a known magnetar, giving researchers their most complete look yet at conditions on the surface of one of these bizarre objects, right as it produced its mysterious signal. That particular observation only became possible because the same magnetar responsible for the earlier burst happened to fire off a second, similar event a few years later, giving 2 completely different NASA instruments the rare chance to already be watching and ready when it happened again. Before that opportunity came along, scientists studying fast radio bursts often had to work backward from incomplete data, arriving at their telescopes only after a burst had already come and gone, forced to reconstruct what happened using nothing but the faint afterglow left behind. Catching an event with instruments already pointed in the right direction, watching the moments immediately before and after a burst rather than only the burst itself, gave researchers an entirely new kind of evidence, showing subtle changes in the magnetar's behavior, called glitches, that appeared to bracket the exact moment the radio burst occurred, hinting that whatever triggers these bursts may be directly tied to sudden, small shifts happening within the collapsed star's own incredibly dense structure. Even more puzzling are a newer class of signals astronomers have started paying closer attention to recently, objects that pulse on a much slower rhythm than any known pulsar, firing off energy every few dozen minutes rather than every fraction of a second. Some of these mysterious sources emit energy across completely different types of radiation simultaneously, radio waves alongside X-rays, a combination that does not neatly fit any previously established category of cosmic object. They behave differently from classic neutron stars, they behave differently from white dwarfs, and researchers currently studying them openly admit they do not yet have a confident, complete explanation for exactly what these things actually are or how they manage to produce energy in such an unusual, slow, steady rhythm. All of this adds up to a genuinely fascinating pattern hiding behind the headlines. Space is constantly sending us signals, some from our own sun sitting right next to us, some from ancient collapsed stars scattered across our galaxy, and some from targets billions of light years away on the far side of the observable universe. Scientists studying a truly bizarre signal from a violently merging pair of galaxies more than 8 billion light years from Earth recently described the source as a hydroxyl megamaser, an extremely rare and powerful natural radio amplifier created when the intense chaos of colliding galaxies compresses gas clouds together in exactly the right way to trigger this kind of unusual emission. Finding one this distant, roughly halfway across the entire observable universe, gives researchers a genuinely rare opportunity to study extreme galactic collisions happening in an era of the universe's history we normally have very little direct data about. Detecting a signal from that far away is itself an almost unbelievable technical achievement once you actually stop to think about the distances involved. Light and radio waves both travel at the same fixed speed, and covering 8 billion light years means the signal researchers picked up actually left its source before our own sun and solar system had even fully formed. In other words, scientists studying this particular megamaser are not just looking at a distant object. They are looking directly into the ancient past of the universe, observing conditions from an era so early that nothing resembling our own planet existed anywhere yet, piecing together a clear signal from a source that faint and that far away requires an enormous, sensitive radio telescope array working in perfect coordination, carefully filtering out interference from far closer, much louder sources scattered throughout our own galaxy that would otherwise completely drown out a whisper this faint arriving from the edge of the observable universe. What ties every one of these stories together is the same basic truth. Real scientific silence almost never means something sinister is being deliberately hidden from the public. It almost always means researchers are still doing the actual work required to understand what they found, carefully checking their instruments, comparing data from multiple sources, ruling out simpler, mundane explanations one at a time, and only speaking publicly once they have something they are genuinely confident enough to defend. The 9-month gap between detecting that record-breaking 19-day solar signal and finally publishing a complete explanation for it was not evidence of a cover-up. It was evidence of careful, patient, honest science taking exactly as long as it needed to take. That patience matters enormously because getting these explanations wrong carries real consequences. Space weather forecasting directly protects billions of dollars worth of satellites currently orbiting Earth, protects astronauts working on the International Space Station, and increasingly protects our own power grids here on the ground, since a sufficiently strong solar event has the potential to disrupt electrical infrastructure across entire regions. Rushing out an incomplete or inaccurate explanation just to satisfy public curiosity faster would genuinely be worse than taking the extra months needed to get the science right the first time. So the next time a headline claims some space agency has suddenly gone silent about a mysterious signal, it is worth remembering what is actually happening behind that silence in the vast majority of real cases. Teams of researchers, often working across multiple countries and multiple institutions, are quietly comparing notes, running the same data through different models, and slowly building toward an explanation solid enough to stake their scientific reputations on. Sometimes that process takes weeks. Sometimes, as we just saw with the sun's record-breaking 19-day broadcast, it takes the better part of an entire year. But when the explanation finally does arrive, it tends to reveal something far more interesting than any invented cover-up ever could. A genuine, verified new piece of understanding about how our universe, and even our own sun sitting right beside us, actually behaves. If stories like this genuinely fascinate you, that is exactly the kind of real, verified space mystery this channel exists to cover. The universe does not need exaggeration to feel incredible. Somewhere out there right now, another instrument is almost certainly picking up another unexplained signal, and somewhere behind the scenes, a quiet team of scientists is already working carefully to figure out exactly what it means. Subscribe if you want to be here the moment they finally have an answer, because based on everything we have seen so far, the real explanation is usually stranger and far more genuinely exciting than anything a headline alone could ever capture. Think about how much has happened just in the story of that one solar signal alone. It started as a single, ordinary-looking burst on an otherwise unremarkable day in August. It quietly refused to behave the way every previous burst on record had always behaved. It kept 4 separate spacecraft busy tracking it for nearly 3 full weeks straight. It forced an entire research team to question their own instruments before finally accepting they were witnessing something genuinely new. And it took the better part of a year of careful, patient analysis before anyone felt confident enough to publish a full explanation the wider scientific community could actually trust. That is not the story of a cover-up. That is the story of what real discovery actually looks like. Slow, careful, occasionally frustrating, and ultimately far more rewarding than any instant answer could ever be. The next time you see a headline claiming some agency has gone mysteriously quiet about an unexplained signal, it is worth remembering this exact sequence of events. Somewhere behind that apparent silence, there is very likely a small, dedicated team of scientists doing exactly what this team did, checking their data again and again, refusing to publish anything until they are genuinely confident in what they found. That kind of patience rarely makes for an exciting headline in the moment, but once the full story finally comes out, as it eventually always does, it tends to be worth the wait. And somewhere right now, whether it is another instrument watching the sun, a telescope array scanning a distant galaxy, or a spacecraft quietly listening near Jupiter, another unusual signal is very likely already being recorded, waiting for its own careful, patient explanation to eventually catch up with it.